Based on our current understanding of regressions, naturally we're inclined to use a linear model to fit the data. In doing so, we're effectively using the linear probability model to answer this question. Let's see what happens when we fit the linear model in this case. This plot shows how the dependent variable interacts with the control variable, the PI ratio. The PI ratio, or the payment to income ratio, is computed using the periodic mortgage payment divided by the periodic income of the applicants. Smaller PI ratios suggest that the applicants can easily afford the mortgage payments, and higher PI ratios suggest that the applicants are having a harder time affording the mortgage payments. Notice that since payments and income are both positive, and the monthly payment should never exceed monthly income, and therefore the PI ratio should always be bounded between 0 and 1. Since the outcome variable is binary, it will only take on the values of 0 and 1. Therefore, when we plot the data, we will see that the data points lie on two different levels, corresponding to 0 and 1, and there's nothing in between. If we fit a linear model on this data, the linear line will look like this. Based on this plot, it's not clear whether we should fit a linear model on this data, but it's still plausible for us to do it. So let's just go ahead with it and see what is the outcome when we fit a linear model on this type of data. Formally, the specification of the linear model is this. As you can see, it's identical to the specification of the linear regression model. The only difference is that now the dependent variable y is a binary outcome variable instead of a continuous variable. If you're using a linear probability model to fit the data, the interpretation of the predicted value of the model changes. Now, y hat, or the predicted value of the model, captures what is the predicted probability of y equals to 1 given x. Hence, beta 1 measures what is the difference in conditional probability of y equals to 1 given the delta change in x. In the first model, we establish our base case. Since the research question is whether race is a factor in getting mortgage applications denied, therefore we create a black dummy that is true if the race of the applicant is black or 0 otherwise. Regressing the binary outcome variable on the black dummy, we measure what is the probability of getting mortgage applications denied when it's a black applicant versus it's an applicant of other races. The coefficient for beta still measures what is the difference in means, like before. In this case, the estimate of 0.191 means that on average, the probability of getting a mortgage application denied is 19.1% higher for black applicants. This variable is statistically significant at 5% level or less. When we added the second regressor to the model, we observed that the coefficient for the black dummy changed. This is because the coefficient for the black dummy in model 1 has upward omitted variable bias. Therefore, by adding the second regressor, the coefficient for the black dummy goes down. Now, how do we interpret the coefficient for the PI ratio? Since PI is a ratio bounded between 0 and 1, therefore I can say that by increasing PI by 10%, the probability of getting mortgage application denied is equal to 0.559 times 0.1, which is equal to 0.0559, or roughly 5.56%. How do we change PI ratio by 0.1 but not by 1 unit? Theoretically, this coefficient shows that increasing the PI ratio by 1 unit, the probability of getting a mortgage application denied is going to increase by 55.9%. However, since 1 unit change is equivalent to 100% change in the PI ratio, therefore it doesn't make sense for you to interpret this coefficient by increasing 1 unit. You have to interpret this coefficient by increasing a fraction of a unit. This way, it makes more sense in the context of this problem. Note that we haven't removed omitted variable bias in this regression, so the coefficients are still biased. You can read this slide and next slide all by yourself. Now let's pause this video and do in-class exercise number 1. In summary, the LPM models probability as a linear function of x. This type of model is intuitive and simple to use. You can draw inferences the same way as for multiple regressions. However, it has two major shortcomings. First of all, it assumes that the relationship between the predicted probability and the x variable is linear. In the real world, it's unlikely to be the case. Second, probability is a measure that is bounded between 0 and 1. The linear probability model allows the predicted probability to stretch outside of these boundaries so that the predicted probability can either be greater than 100% or become a negative number. This is obviously not realistic. And therefore, to do away with these shortcomings, we need to use either the probit model or the logit model.